Hi, I'd like to present my in-the-field project for the cloud computing course Harum. Harum is basically a laundry marketplace, but it is designed specifically for the Indonesian market, where a portion of the laundry outlets are still conventional. That is, it is the outlet staff who actually washes the customer's clothes instead of the customer themselves. And this business process actually produces a problem, especially during the festive seasons where the laundry demand surges. Laundry outlets becomes overwhelmed in handling the orders, and thus they start to reject or even provide a far-fetched completion date for the orders. And this leaves the customer to struggle in finding the nearest laundry outlet that is still capable of serving their request. And hence comes the idea of Harum, which allows customers to view all laundry outlets around them, sorted by distance, and submit their orders online, such that it is guaranteed that the laundry is capable of serving the orders once the customer reaches the laundry location. Harum application is decomposed into 5 microservices, composed of 1 front-end microservice and 4 back-end microservice, in addition to 1 database service. The front-end microservice here is responsible for serving the static files containing the front-facing portion of the application to the user, and it is deployed using Nginx. The gateway service, on the other hand, which is developed using Python, Django, and run with Unicorn, is responsible for acting as a single point of entry of all requests sent from the front-end service, which performs authentication and authorization, then redirects the request to the appropriate microservice. Now, the gateway service here also communicates with the Firebase service to perform the authentication. Now, the outlet service here is responsible for managing the logic relating with the display and storing of outlet data, including outlet registration and outlet discovery that provides a list of outlets along with their registered details and services. Now, the customer service here is responsible for managing the logic relating to the customer data. And finally, the order service is responsible for performing the logic for laundry order creation, update, and retrieval. Now, as you can see here, the application uses MongoDB as the database, and it is chosen due to its support for unstructured data, allowing the application to store data that is used in tandem together, such as the laundry receipts and the order entity, such that they can be used together without having to join the two tables. In addition, it also provides consistency, which is very useful for this application, given that the application involves a lot of concurrent modification of outlet data when multiple users try to submit an order at the same time. As you can see, the application is deployed using Kubernetes, and the complete list of used technologies are shown in the bottom of the slide. Here's the database design of the application, which, as you can see, composed of 8 entities. The one in blue deals with the outlet service, the one in yellow deals with the customer service, and the one in red deals with the order service. But despite it is shown as in a relational manner, the actual data in the application does not have foreign key linkage, as they are actually stored responding to each microservice. In addition, the actual implementation, as discussed earlier, also groups the laundry order receipt here with the laundry order as an attribute of the laundry order, as they are often used together. Now, I will demonstrate the functionality of the application, starting with the customer functionalities. Here, we are in the login page, and after we input the credentials, the application should redirect us to the user explore page. Here, the customer can view the list of outlets available in the application and input their location or the name if they prefer to. When the customer input the location, for instance, Northwest Building here, as you can see, the list of outlets becomes reordered based on the distance to the location. Here, Great Court is shown first because it is actually closer to Northwest compared to Hawken Engineering Building. Or if the customer wishes to search an outlet of certain name, they can do that by inputting the name in the search bar. If they were to find outlets matching the name Hawken, they can do that by typing Hawken. And as you can see, only outlets matching the name Hawken will be displayed. The next functionality that I'd like to present is viewing the services provided by the outlet. Here, for instance, this can be done by clicking the Order Now button. As you can see, the list of services provided by the outlet is presented here. If we switch to the outlet's application, we can actually modify the services by using the Add Service button or Update Service. For this demonstration, I'd like to actually update the price of the provided service. For instance, blazer here from 16,000 to, for instance, there's a discount to 14,000 rupiah. And this can be done here. As you can see here, after the update, the price is actually updated. The next functionality that I want to demonstrate is the order. When the customer submits an order that exceeds the quota, the application will reject the order. As you can see here, it has reached the maximum workload. This is done to ensure that the outlet is not overwhelmed and that the customer can always submit an order when they arrive at the location. For instance, if they submit an appropriate order here, consists of t-shirts and 2 jeans, for instance. As you can see, the order is successfully registered. And after it says that the order is successfully registered, as you can see here, the item is actually presented in the list of orders here with the status pending. Looking back to the outlet application, the order is actually registered here with the same price and status. Here, I'd like to demonstrate the functionality where the outlet can actually update the status of the order. For instance, once the order has been sent to the location, they can change the status to receive. This status change is also reflected back in the customer's facing app of the application. As you can see now, the status is received. The final functionality that I'd like to demonstrate is the ability of customers to provide a rating to the completed orders. For instance, I can go to the completed tab here to view one of the orders. Here, I haven't submitted a review for this particular order. Now, as you can see, I can submit a review. For instance, if I were to submit 3 out of 5 and say the order was not completed in time, for instance, and submit this review, it will say that the review for order is created successfully. And most importantly, if we travel back to the Explore page, you can see that the overall rating of the Great Court Laundry is updated, and we can actually view the review being submitted to the Explore page. Now I'm going to demonstrate the cloud computing characteristics demonstrated in the project, starting with scalability. As you can see in the list of pods here, each deployment actually only have one pod. But for instance, when there is surge in demand and we need to scale the front-end services, we can do this by simply typing kubectl scale deployment and then Harum FA deployment, which is the name of the front-end application deployment, and we set the replicas into 3. Now, by listing the pods again, we can see that 2 containers are being created to keep up with the demand. And this shows that the application is scalable. The next component that I want to demonstrate here relates to rollout and rollback. So for instance, here we have this term laundry outlets, but we want to change this to use the word laundromat. And this can be done by referring to a new image that I've created with the tag updated. So to change the image, we can simply say kubectl set image, and then after that, deployment, RMFA deployment, and finally the name of the container with the new image. With the tag updated here, as you can see, the deployment is being updated, and we can see the rollout status. Now it is successfully rolled. To demonstrate the changes, let's open a new incognito tab. Now, as you can see here, it says Laundromat. But for instance, there is a problem with this application and that we want to refer back to the previous version. And this can be simply done by typing kubectl rollout undo deployment, Harum FA deployment. We can actually view the status. Now that it's completed, we can actually reopen the page through the incognito tab. Here, as you can see, the term is reverted back to laundry outlets, which shows that the application allows rollout and rollback. The final component that I want to demonstrate is reliability. The ability for the application to function despite having failures. To demonstrate this, I will start by scaling the gateway deployment to use 3 replicas. As you can see, the deployment is being scaled, and when we see the pods, you can see that 2 containers are being created. Suppose that we kill one of them to demonstrate pod failures. Now, when we view the list of pods, as you can see, a new pod is being created, and this is due to the fact that Kubernetes is able to detect the mismatch between the desired state and the actual state, allowing self-healing. And when we go to the page, it is shown that the application still runs despite the failure, either due to the redundancy or self-healing mechanism. And this shows how the application is reliable. So that is all that I want to demonstrate for my individual project, which highlights the cloud computing characteristics in the application. Thank you for your time.